So have you, can you see my screen okay, Ilona?
Yep, it's crystal clear.
Okay. And so I think I'll go ahead if that's okay. Yeah. Okay. So I'll introduce myself first. I'm Mark Chignell. I'm a long-term professor at in mechanical and industrial engineering at the University of Toronto, but I started out in psychology. That's where I got my PhD, and then I got a master's in engineering. So I consider myself a kind of a failed psychologist, perhaps. And when I did my master's back in 1983 at Ohio State, I did a master's in artificial intelligence. At the time, it was all about expert systems. So times have really changed. And now we're looking at, a lot of deep learning, generative models, and so on. But there's a huge interest in AI. And I think it's fair to say that whenever there's a technological, breakthrough or change, whether it's graphical user interfaces or visual display terminals in the old days, or the World Wide Web or smartphones, it creates challenges and an opportunity for better design and better integration with people. So we're always going to see these waves of interest in human factors and human computer interaction coinciding with these technological epochs. And the latest one, of course, is AI. And I think it raises just a huge number of issues about how people should interact with AI. And that's really the topic of the talk. And I'll talk about sort of different models and approaches and give you a couple of case studies. Oops. Okay, first challenge, get my slides to advance. Okay, so I'll talk a little bit about the human brain, but not too much. I teach a course on cognitive neuroscience, which basically tells engineers about the brain. And so I'll take a little bit from that. And then I'll talk about the challenge of AI and some of the models that people are developing in terms of how humans interact with AI and vice versa. And then I'll talk a little bit about interactive machine learning, and I'll talk a little bit about and human AI interaction. And I'll look at two case studies. I've been involved with healthcare and cybersecurity. And then I'll talk a little bit about future prospects, and I'm hoping we can have an interesting discussion. So a lot has changed since the late 1980s. This was a model, I think, created by Stu Card back in about 1980. And he was trying to develop this thing called the model human. And the idea was that everything was based on timing because that's all people knew about at the time. So it was great if you were trying to predict reaction times, but pretty lousy at trying to do anything else like predicting accuracy or predicting complex task performance. So this approach was too early, and it failed to cover what we've since learned in brain scanning. So that was an early attempt to try and understand the human brain, which I don't think really worked. In general, we've had this idea that the cortex is everything. So I remember when I was a kid seeing these sort of Time Life sort of TV shows about the wonderful brain, and you'd see a brain spinning around, and all you could see was the outside of it. And we never really knew, even on the outside, like where different things were. And so this wonderful brain idea, I think, is a little bit misleading. What we should do is, think of the brain as a machine and get down to the details. So in the 1990s, we started getting brain scanning. And for the first time, we were able to see inside a living brain and could see functioning at the level of, different levels of activation in different parts of the brain as the brain responded to different task situations. So this was really exciting and created a revolution. And for me, it was really interesting because when I was doing my PhD in psychology in the late 1970s, there was no such thing as brain scanning. So everything was kind of black box and descriptive. And I came back and I was asked to teach a course on psychology for engineers in 2010. So I went back and looked at the psychology literature and realized that, everything I'd learned in grad school was largely irrelevant. I mean, there was a few things, obviously, like experimental design and stats, which were fine, but so much about my understanding of the brain was old school and had to be updated. So this is just a quick figure showing the wiring in the brain. So the brain is old school. It looks a bit like a Bell Canada sort of switch box, and it has all these fibers and tracts going from one side of the brain to the other. And these carry information very fast, maybe 10 to 20 milliseconds across the brain. So vast distances in terms of, brain size are covered very quickly. And what this means is there's a whole lot of crosstalk. And this is kind of why you have the brain waves, because you get these resonant sort of networks sort of maintaining active information. And then you have all these timing issues in the brain. So it's like a horse race model where you have to like get something to happen at the right time window. So it will then meet some other activation and in turn sort of trigger a new process. So the brain has all these complex timing issues based on its structure, which is very much an analog structure with wiring. Okay, by the way, the wires look kind of white. They don't look gray, or they don't look purple or green. That's just color coding here. So, but the techniques, they have some very interesting techniques that are used to be able to visualize these wires. Okay, so here's a picture of a brain with a slice. And what's highlighted here, the green part, is the hippocampus. This is the memory system, and this is subcortical. So this is an example of stuff that is not, inside the wonderful brain that you can't see if you're just looking from the outside. And beside it, are some other structures, and just below it is the brainstem. And the white parts of the figure, all the white matter. So about 50% of the volume of the brain is to do with transportation. So if you think of the gray matter as the cities and towns and factories, then the white matter is logistics and transportation. And so generally you have the cortex you can think of as like a yoga mat, the same size as a yoga mat, that's been folded around all the transportation white matter. Okay, so that's our brain. That's what we have. And this is what we have to deal with when we're trying to solve complex tasks. Now, it turns out that a lot of our brain has come to us through evolution. And so, we have a whole lot of processes inside the brain, some of which are millions of years old. And for instance, if you look at basic emotions like fear, as I think this groundhog or whatever it is experiencing with the Arctic fox behind it, this is, wired in. It's part of the brain called the amygdala. And we have that same amygdala, and so do pretty much all other vertebrate animals. So this is a very ancient structure that processes fear, and fear has a lot of survival value. So, it's good to be fearful most of the time. So this just shows the memory system again, right next to the fear system. So just showing you how important fear learning is. So basically, we want to avoid things that are fearful, and the system is built to do this very rapidly. So we see again this specialized circuitry in the brain. And what we see generally is that there is a kind of a low road, which is very rapid processing of information. And it seems the way the brain works is that every perceptual input is screened for whether or not it's fearful or opportunity providing. And we have this very emotional response, which is always ready to go. Most of the time, it's not triggered because we're not looking at a spider or a snake or whatever we find fearful. But occasionally it is triggered. And then we go into kind of an automatic mode. We kind of fight or flight. On the other hand, the high road is where information goes to the cortex and is processed in a more rational way. So again, we have all these systems, these ancient systems in the human brain, along with sort of somewhat more modern systems, which are more associated with primates and great apes. So the brain is actually a bunch of co-processors connected by a fiber network. And some examples are in the frontal cortex, there are the frontal eye fields, which plan eye movements. In the inferior temporal cortex, which you can see here, in the light blue, we have face processing, and this is on the underside of the brain in the temporal cortex, and this recognizes faces. So we have these specialized areas, which you can think of as co-processors. These two are cortical co-processors, and then in the subcortical regions, are sort of around the brainstem, we have the hippocampus, which is a memory co-processor, and the amygdala, which is an emotional co-processor, but in particular, it processes fear, but many other things as well. So we see here that the brain is basically an expandable architecture that has been designed to be a kind of coordinating group of co-processors. So this suggests that AI can be yet another coprocessor for the brain. And, the architecture seems to support this. So here we see the idea that the brain has been built through evolution. And you can think of evolution as solving a succession of increasingly challenging problems as an animal experiences more competition and has to live in a more complex environment. So you can think of, like bacteria, it's a very simple perception action cycle where you need some kind of perception in the earliest stages, chemical perception that looks for food sources and avoids toxins and predators. And then you have a kind of action motor system which initially consists of flagella, which allows you to move towards things you want and away from things you don't want. You can think of this as the origins of emotion, where you have like a approach avoidance. And then as animals became more complex, there was the notion of having to survive, again, in a predatory environment. And so you had to have first fear and then increasingly other emotions as, things became more complex. After that, the animal needed to learn. And so you have a kind of reward processing system, which is a lot like the reinforcement learning process used in AI, which is modeled on the human brain. And basically, you learn through a dopamine-based system in the brain what things are rewarding and what things are punishing. And then you change behavior to try and increase the value of the inputs you receive. After that, there's more complex learning again. And now we're looking at memory systems and, watching a squirrel hiding nuts is an example of an animal using a memory system. There are different kinds of memory. There's procedural memories where you learn how to do something. And then there are declarative memories where you learn semantic or biographical information or episodic memory being things that you've experienced. Later on, again, we have more complex environments. So where we have to start doing decision making, people have to choose which grad school they go to, what career they're going to have, where they're going to live, and so on. And then, apologies for the typo here, we have even more complex environments. And this is where we're going to need AI coprocessors and agents. And this is what I'll be talking about. Okay, so in my view, AI is another step in the evolution of the brain. It's just another coprocessor. And you can think of a mobile phone as a handheld coprocessor, a voice agent as a wireless audio coprocessor, and AI is now a cognitive coprocessor. Now, this is AI as an augmenting technology, but it's just one model of how we interact with AI, as you'll see. So we have a model of human AI interaction where AI is a co-pilot, and this is a term that's been pushed by Microsoft recently, and it uses the analogy of aviation, where you have a pilot and a co-pilot working together. We can also think of AI as an independent agent that we interact with and collaborate with, or as a master. And I don't mean in the sense of an overlord, like a Sith Lord, or maybe a Sith Lord doesn't make sense, because I think of it more as an apprentice-master relationship. And after a while, the apprentice is trained to a level that it also becomes a master. And finally, we can sort of talk about AI as a cognitive coprocessor, augmenting the brain. And ultimately, I see this as an implant. So we can imagine a situation where, parents, instead of just sending their kids to the best schools, give them an early brain implant so that they can learn more quickly. Okay, so this is a paper that's been placed in archive. And, I believe it's been submitted to, I know it's been submitted to another journal because I reviewed it. And it's from Abby Sellen and Eric Horvitz at Microsoft. And Abby's the research director at the Microsoft Research Center in Cambridge, UK. And they're basically using lessons from aviation. But their approach, which I don't fully agree with, is that we should always keep people in the loop and that people should be the final arbiters. So they argue strongly for not having over-reliance on automation. And I think this works perfectly well in some situations, particularly transportation, but may not work as well in other situations where people are trying to make rapid decisions and where we know that the model is good. So we'll talk about that. So I've recently put out a paper which is currently under review, looking at the idea of model mastery, which is, when models become masters, when they go through their apprenticeship, they're trained by experts, and then they outperform the experts. And what's been found over many years, first reported by Paul Mail back in about 1950, is that in many situations, simple models can outperform experts. They're more reliable, less noisy, less emotional. And in fact, there are many studies to show that experts not only disagree with each other, but often disagree with themselves, giving different decisions on the same case at different time points. So in spite of that, most experts continue to make decisions, especially in places like healthcare, even though there's increasing evidence that perhaps they shouldn't. So this is an old figure from Bill Buxton. I'm sure others had similar figures at the time. And this is the idea that, with evolution being very slow and maybe even going backwards. I've been watching undergraduate students. One of the privileges of teaching a whole bunch of undergrad students each year is you get to see changes in time in the student population. So what are adolescents doing? And what I noticed was, over time, continuously since I've been at the University of Toronto over the last 34 years, the number of pages that people would write in exam papers kept getting shorter and shorter. It'd be 3 exam booklets, then it was 2 exam booklets, then it was 1 exam booklet, then it was a half exam booklet. And then I switched to electronic text and it became, 1 page of copied text, 2 pages of copied text, and 3 pages of copied text. So people really don't seem to write that much anymore. And it's not just me, because I've read studies which suggest that the world IQ, which has been generally rising over from one decade to the next, seems to have been reversing in the last 10 years or so. And I am suspicious about the role of smartphones and these technologies, which basically give people the sense they don't need to learn because all the information is readily available in the device. And as a result, I think fluid intelligence may be suffering. Okay. So this is just a picture of Paul Mail, and he asked a question in 1954 about which is better, clinical judgment or actuarial judgment. Actuarial judgment in this case is the model, and he said that in many cases he did a survey of clinical and actuarial decision making. He showed in many cases the model outperformed the expert, and that's been found many times in the decades since. Okay, so let's go to switch gears. So we have the idea that the human can use AI as a co-pilot. We have the idea that humans can train models, which can then serve as masters in a particular narrow field of an area like decision making. And then we have the idea of the co-processor, which we can think of as a way of augmenting people. Now, this is an old idea that goes back to Doug Engelbart, and everybody talks about, the augmented human and how Doug Engelbart had this idea originally. So I went back and looked at the original paper from 1962. As you can see, it's mimeographed. And what I found was it was a very simple concept, which I don't think provides us with any design insights. So you'll see here that there's the outside world that we're communicating with. And on the left, we have the human process. And on the right, we have the artifact, which we would now probably call the AI. And there's some kind of matching process, and there's some kind of user interface, and then there's some kind of energy flow, and somehow these things get together and then they act on the outside world. Now, I don't know about you, but I don't think I can really design anything here. I mean, I know there's got to be a user interface, and I know there's got to be outputs and inputs from the outside world and outputs to the outside world, but I really can't see any design relevant information in this diagram. So it's clear that, while the idea of augmenting human intellect was a good one, as of early 1960s, people who were thinking about this had no idea how to implement it. Well, times have changed, and we now have a lot of technologies and a lot of experience, which gives us more knowledge. So automated driving is an example where the human augments machine capability. And the idea is if the machine can't do the task, then the human takes over. But just a footnote that, in the 1960s, we didn't think that people were going to work so hard. Honestly, we thought that the main problem was going to be leisure time, that people have ridiculous amounts of leisure and they wouldn't know what to do with it. Kind of like everybody retire at the age of 20 after they finish their education. And they thought that, AI and other technologies would make us more powerful by augmenting us. So, we could sit back and relax. But this didn't happen. In fact, it seems like, tools like email have just made us work harder. And there's also, of course, the comment that, that there's been a huge concentration in power. So the technologies seem to just be disproportionate in their effect on people. So unskilled labor, for instance, has become much less valuable than it was in the 1960s. But let's look at automated driving as a test case and think about, this relationship between human and machine augmentation. So this is the standard idea about levels of automation in driving, and I think this SME produced these levels. And so let's look on the left. On the left, we have a conventional driver at level 0. So the human is doing everything. And on the right, at level 5, the human is just a passenger and the automation does everything. And in between, we have various shades of cooperation between the human driver and the vehicle. So you can see at level 1, we have an enhanced driver. Maybe we're sort of at this level at the moment where things like, automatic braking and cornering, sort of guidance around corners and so on, is meant to enhance the driver. Now, personally, I use car share, so I'm using lots of different models of cars, some of which are recent, and I find it very annoying when the car tries to turn the corner for me, and I'm kind of fighting it a little bit, so the steering wheel is no longer smoothly under my control. But other people, especially younger people, seem to like these features. And then, we have this idea at level 2, we become an automation supervisor. Level 3, we become a co-pilot. And then at level 4, we've pretty much become a passenger, and maybe we're just providing a few instructions. So this is how the role is changing on the top for the human and lower down for the vehicle. So the problem is that, when it's mixed initiative and mixed control, that's when we have this human factors problem. So human AI interaction matters in these intermediate stages when the person is no longer completely the driver, but is not yet completely the passenger. And in this case, you have to look at how to help the vehicle assist the driver at stage 1, at level 1. And then level 2 and level 3 in particular, you have a need to create a kind of synergy between the vehicle and the driver. So it's particularly dangerous, if the vehicle finds that it's outside its design tolerance and needs to hand off the control of the vehicle to the passenger, because if the passenger is busy watching, a 2-hour movie and not monitoring the road, the driver acting like a passenger, or the human acting like a passenger, then they may not be able to pick up the pieces and get out of a tricky situation because they simply don't have enough time to react and to rebuild their situational awareness. So this is a paper. This came from a paper that Sachi and Peter Hancock and myself and others wrote a couple of years ago, sort of summarizing this issue. Okay, so human factors is going to be important for human vehicle interaction and interaction with automated vehicles. So that's just an example of how, new technology and AI in particular is creating opportunities for, problems that human factors and human computer interaction people need to address. So this is from a paper I did last year, which kind of motivated this human interaction talk, AI interaction talk. That was in the ACM transactions on computers and human interaction. And on the left, we have a kind of a human side of things. And on the right, we have the device or system, could also be an AI agent. And what we see here is a sort of information or task processing stack going from the initial sensing all the way to execution. So we can imagine, we have this stack. We start off with sensing, we go to perception, interpretation, computation, assessment, decision, execution. And we can imagine that things are handed off from one side to the other. So the human might start off acquiring the information, and then, or in this case, the dark blue indicates the agent that's doing the work. So in this case, the system or the AI device is sensing and perceiving, interpreting, and doing the initial computation, and then hands over the results to the human that does some assessment and decision making before handing back to the device to do the actual execution. So in a model where we have AI agents, we need to sort of figure out these flows, and I think that this kind of flow between which initially we called mind meld, kind of Vulcan mind meld, the idea of the agent and the person have to work together, and they have to know where they are in the task processing stack in order to hand off and receive successfully. So let's talk a little bit about interactive machine learning and try to make this a little bit more concrete. And we'll talk about the problem of trying to train an AI system. So there's a subset of the human AI interaction problem, which is associated with interactive machine learning, and it's a big subset. And we could, everybody who does HCI could probably sort of go to this problem, and they would give them enough work to do. So here's a simple view of machine learning. We have an input, and we have some kind of prediction we make, and it's passed to humans, and they give some feedback. Now, in one model, they actually provide labels. In another model, they critique. The end result is the same. And they provide the feedback, and then we incorporate the feedback into an evolving machine learning model. And eventually, the model makes better predictions based on this human training process. So machine learning models are generally trained. Either they're trained by humans explicitly, or they're trained by some kind of evaluation criteria that is applied, automatically. The classic example of interactive machine learning training was a very clever system developed by von Ahn, and you probably know about it, which was for Google Image Labeler. So he used to have a system called ESP, and the game, if you've ever played this one, was that you'd have a game with a remote person. You'd both see an image, and then you'd generate a bunch of words to describe that image, and you'd get points. The two of you would get points based on the amount of agreement between the words you gave to describe the image. So obviously, this game was a great way of getting humans to label pictures, and so they labeled, presumably hundreds of thousands of images, and they had a criteria where they would use a bunch of judgments, on the same image to try and improve the reliability of the method. And after that, all those labels became part of the machine learning process, and from that, they could start labeling new images. So that was the example of a kind of a machine learning approach with Google Image Labeler. Okay, so it's a very powerful method. It's been very successful, and arguably one of the sort of there are probably two sort of approaches that have been dominant recently in AI that's sort of created this kind of aura around it. And one is machine learning, and the other is generative AI and the use of large language models. So these two things are probably, when people talk about AI and how wonderful it is, this is generally what they're referring to. So let's talk about healthcare and do a little bit of an interactive machine learning case study. And this is work that we've done with St. Michael's Hospital and the Gemini team. So Gemini is a very large health data repository, and it has billions of records from, I think, up to about 20 hospitals in Ontario now, and it's growing all the time. So it's a great resource, focusing mostly on internal medicine. So this is work that I did with Lu Wang, who did a PhD in my lab, and she's now an assistant professor at the University of Houston in the med school there in biomedical engineering. In this kind of framework, we can imagine a sort of user-centered design process first, followed by a technology acceptance evaluation, followed by implementation and product release. So there's nothing different about AI products and human AI products, if they're going to be used in the real world, and they should be. So we're not talking about research now, we're talking about application. Then they have to go through, releases and formal processes for acceptance and so on. So this on the top there, you see the familiar iterative design cycle with design prototyping, evaluation, and requirements engineering and design and so on. And then in the middle, we're looking at the technology acceptance model or TAM, and this sort of measures intention to use and so on. And then finally, we're going to have to do implementation science in the case of healthcare or just general, deal with product diffusion and differentiation and improvement in a sort of general marketing situation. So human-centered AI or human AI has to fit into, normal processes. So this is an approach we developed with physician experience design. So just as we have user experience design, when physicians are working with clinical decision support tools and AI, we need to design the experience for them. And so in this example, we start off at the diagram at the top, and we've got a bunch of different machine learning models. We don't know which one's going to work best generally. We predict the results, and there's a bunch of evaluation metrics saying how good this is. And in our case, we were trying to predict delirium based on charts, because often delirium goes unrecognized in hospitals. In fact, we came up with a model that's being used at Sunnybrook Hospital to measure the quality of their delirium prevention programs. So, we're kind of proud that this is actually in use. So you come up with the results, and then you do design to try and make the provision of the results to the physician more effective and consumable. And you might do some conceptual investigation with questionnaires or focus groups and interviews to try and understand, the physician requirements and to what extent, we need to change the visualization of results. And then there's going to be some kind of technical investigation, also looking at the adequacy of the predictions. And then we're going to show some kind of dashboard, and we're going to evaluate how effective it is with the physicians. They're going to rank the alternatives. They're going to select the models which seem to be giving the best results and so on. And I've got a very sort of simple kind of interface shown below, where we have a questionnaire. At the left, if you look at the lower part of the slide with the sample figures, on the top left we have a calibration plot, which just tells us the extent to which the sort of percentage estimated by the model reflects the percentage of cases that do or don't have delirium. And ideally, you want that to sort of fall on the main diagonal of the plot. So we found out that physicians care a lot about calibration in models, and just as much as they care about accuracy. And then we can look at a dashboard. If you look at the third from the left, that says physician experience design, we might have a number of drop downs and choices that a physician can make as to what's important, or to choose different options. Okay, now this is not to say that we know what physician experience design should be. I mean, it's still a very recent concept, but there is this whole issue for healthcare AI in terms of how you make the AI consumable, and how you train the model more effectively, how you evaluate the results more effectively, and how you use the results more effectively. And each of these raise user experience issues. Okay, so one of the things we did was in our model of delirium prediction was we used text sentiment analysis to improve the prediction. So we looked for the words that clinicians use to describe cases that are later labeled as having delirium. And then we used machine learning to create a feature that measured delirium sentiment. And after that, we used that feature as part of a model that predicted the presence of delirium. And we asked the question, how much does delirium sentiment boost the model? And these are some of the results. What we did was we were using tenfold cross-validation. And we also had a holdout test on the 10th time period, but I'll just show you the time progression here. And this kind of plot is useful in machine learning because it tells you whether you have a stable model or whether the model is showing drift. So if a model is showing similar evaluative performance across all the time-related folds, it suggests it's pretty stable. So here we see a pretty stable model. It's more stable in terms of some of the features. So if you look at the evaluation metrics, it's accuracy on the top left, recall on the lower left. This is a binary decision task. So we can use measures that are similar to the measures used for looking at relevance in text retrieval. We can look at the F1 score, which combines recall and precision. There's also the area under the curve, which is the middle of the lower row. And we can look at precision on the top right. And here we see that precision doesn't really benefit that much from, or at all, from the sentiment feature. But all the other ones benefit, with the blue being above the orange line. So we see here that, if we use sentiment analysis, and sentiment analysis is really clinician based because it's the clinician's text that is driving the machine learning model. So obviously, we can use human AI interaction can be synchronous and in real time, or it can be asynchronous, and we can have stored knowledge being fed into the model. So a lot of these very powerful large language models, are using large text corpora, like existing text, and then they're also using the questions that people ask as a way of training the model. Okay, so that's physician experience design, a very quick overview. I'll now go to and I see that time is progressing, so I'll make this quick. I'll now look at interactive machine learning and cybersecurity. And this is work we're doing with a financial services company. We see here that in the traditional view, we have domain experts talking to machine learning experts, and machine learning experts set up the machine learning model. Now, this is kind of wasteful. And back in the 80s, I co-authored a book on expert systems for experts. And the main message of that book, or one of the messages, was, look, it's much easier to train an expert to, build an expert system than it is to train a computer scientist, to have a medical degree. Right? And the same thing is kind of true here. It's much easier to take a doctor and explain the basics of how to build a machine learning model than it is to take a machine learning expert and train them to be a doctor. So, it's not really very efficient to try and get the domain experts to train the machine learning experts in this way. And so the idea of interactive machine learning is we cut out the middleman and we go straight to a communication between the domain experts and the machine learning model. But obviously, to do this, we have to make sure it's a good interaction and we have good user experience so that domain experts can do what they need to do without having to be too involved with the technical details. So what are people doing in interactive machine learning? Well, they can be suggesting features, choosing samples, applying weights, providing labels. So essentially, saying what's the correct decision in a training set. The system can be bringing back predictions, classifications, visualizations, and queries, which again, the person can provide, or the domain expert can provide feedback on. So we have this loop where you can think of the domain experts as complementing, not in terms of saying how good you are, but in terms of providing a different set of skills, the machine learning. So the machine learning model will tend to have different strengths and weaknesses from the human experts. And that's why human AI interaction can be so effective. In cybersecurity, one of the big problems is data exfiltration. And this is where people come inside the firewall and start, grabbing data. Much of the cybersecurity apparatus is concerned with protecting the firewall. But if you have a phishing exploit, often what will happen is an account within the company will get compromised. And at that point, the firewall is not an issue. What is an issue is detecting the behavior of the compromised account and, shutting it down before it does any damage. So in this partnership between the expert and AI for cybersecurity, the experts will be providing inputs, analyzing results, calibrating expectations. And then within the middle there's an issue of compatibility. How can create an interface where they can talk to each other effectively? You can think of it a bit like the gulfs of execution and I think was it perception? I can't remember now that Donald Norman talked about in his Design of Everyday Things book. And then over on the machine side, we've got the goals of minimizing misses, reducing false alarms, and providing explainable input output. And one of the biggest challenges at the moment, which everybody recognizes, is explainable AI. And I would say current approaches, which are based on feature importance, are extremely rudimentary. So we have a long way to go to make AI more explainable. And people are trying to apply large language models to this problem, but I think I don't yet see terribly good results. Okay, so here's some use cases. A compromised account may have the following anomalies. Unusual login IPs from multiple continents on different days on the same day. Suddenly starting up and sending emails to too many other employees, unusual log times, and so on. And I run the TorCHI Facebook group, and we have these two chats, and these chats allow people to come in and just send messages. So they just have to create an account and they can start sending messages. And of course, this is a great tool for spammers. So I have to sort of shut down the spammers. So the first thing I have to do is see if I see someone new suddenly starting sending messages, and the only message is a link and there's no text. I will ban that account right away because it's obvious that it's not going to be a real person. Okay, so one of the dilemmas is that people may not be malicious. So we might just have, unusual behavior that's benign. And so we have to distinguish between this benign behavior and this malicious behavior. And it's troublesome because manually it takes too long, but machines often generate a lot of false alarms, and it's, you need the human to come in and distinguish between the true anomaly and the benign behavior. So in this case, you have your model, and then you have domain experts which are helping to label and provide feedback. And this is probably the best way to deal with the situation. So now people have talked about the use of active learning. So this is a very popular technique. And the idea is that you try and prioritize the cases that the domain experts have to label so that the process is more efficient. So instead of just randomly selecting cases, what you do is you choose cases that are likely to maximize the reduction in uncertainty that the model experiences. In other words, the cases that will train the model the quickest. So you want to prune false alarms. You want to have a form of active learning that people can work with smoothly. And you want to assist the labeling process. So even here, there's lots of interesting human factors and HCI questions. So this is just a model of a binary decision-making task. And the dotted line is showing a kind of decision boundary. And the orange, I don't know if you can see the colors very well, but if we have red and blue as the two classes where we've labeled, then we have a lot of uncertainty. And the cases, the clear cases that are in the sort of class 0 and close to the blue cases, they're not going to be very informative because we know that region of the decision space. And the same over on the red side. But near the decision boundary, we're going to have a lot of uncertainty. So what models do now, active learning do, is they tend to focus on the decision boundary. But the problem they face is that if the model is having trouble deciding on a case and it's uncertain about it, maybe the human is also having a problem as well. So you're not going to get much advantage by having them label those cases that they're also uncertain about. So this led some work that was done by my former student, Miles Chung, who got his PhD last year. And he developed this approach of high information gain. And if you look in the, if you think about the model, it can either have low or high uncertainty, or low or high certainty, and the person can have the same. And the sweet spot here is situations where the model has low uncertainty and the human has high uncertainty. And there we get high information gain when the human labels the case. So active learning should be looking for the sweet spots. And what we do is we use confidence judgments. So every time the expert makes a label, they also give a confidence judgment. And that way we learn, we're able to learn what makes the person confident, and we can predict the confidence of a new case. So we have a separate process that predicts the confidence. And then we provide cases for labeling that maximize the difference between the model uncertainty and the expert uncertainty as predicted by previous confidence judgments. And here you'll see some data that was collected at this financial services company with human experts. And we see that the information gain heuristic, which is the green line, gives us the best performance. And obviously things are bouncing around, especially in terms of the expert performance, which is the blue line. And here, this is just a simple line chart showing that there's sort of a big improvement in, from 0.6 F1 scores to close to 0.7 for the information gain heuristic. There's a slight improvement in experts, but the baseline model, which is without our approach to active learning, also improves, but only to the level of expert performance, at the number of rounds we used in this study. Okay, so in the real world, we have a lot of complexity. I've almost finished, and we have a socio-technical problem, lots of paper, lots of screens, lots of people, lots of things happening, and we have to figure out, how this person is going to fit into that process. I don't know where I got this from. I know I borrowed it from someone, but if it's yours, I apologize. Okay, so there's going to be key human factors issues that haven't gone away, and so it turns out that that I think there'll be a renaissance in human factors. It's not just about power plants and driving and flying. I think it's going to be about AI in general. So we need to know how we can make people trust and rely on AI appropriately, and we can calibrate the trust. We need to provide people with situational awareness. We need to manage workload. So what will tend to happen is when people have AI tools, then their work tends to expand because now they have more time. So we just have a different kind of problem. It reminds me of when they created anti-lock braking. So they had anti-lock braking, but surprisingly to the designers, the number of accidents didn't go down because what happened was people drove more aggressively because they adapted to the anti-lock braking. So I suspect that workload may be a similar issue. And then we have the idea of supervisory control. You see that in the automated vehicles, where the person is going from transitioning from a driver to a passenger, but still has to exert supervisory control. Also, we see it with physicians managing automated clinical decision support systems, where the automated system may make a recommendation in the electronic health record, and then the clinician has to decide, whether or not to accept it. We also have safety issues, fairness, bias, many issues that I think that human factors has or human computer interaction has a role to play in, and then the whole problem of interruptibility and distraction when tasks are no longer continuous and where AI agents are interacting with people. It's like if as an example, if you're driving, this is an example that we've been working on called a safe driver notification. If you're driving and you have like social media and email and voice, notifications coming in, when is it safe to interrupt the driver and tell them about these notifications, and when should it be delayed because of the complexity of the current driving task? So all these issues are coming back and becoming more important. So it's a great time to be somebody working in the domain of human factors and human-computer interaction. So to conclude, human-AI interaction is one of the central problems of our time. And for the moment, probably we're actually focusing on augmenting AI, not on augmenting humans. Maybe that's a good thing because, augmenting humans is a little bit scary, and probably we should be careful about how we do it. Obviously, some people believe in the singularity and the idea that AI is going to take over. Some people believe that large language models are producing behaviors which are a little bit scary and that we should stop developing AI. But, it's always hard, right? I mean, cars used to scare the horses, but that didn't stop people developing them. So, it's hard for me to see people are backing off on the technology development. There's too much money to be made and too many people who are curious. So why focus on interactive machine learning at the moment? Well, machine learning is a powerful set of tools with good results across many applications. Things like physician experience design are critical to effective use of machine learning in healthcare. And healthcare really needs AI because it's understaffed and it's complex and people are tired and they often make, the wrong decision. 100,000 people every year die in the US supposedly because of medical errors. So yeah, we definitely need to improve things. And similarly, for cybersecurity is another huge issue. There are lots of state actors now that are hacking away. Every year in hospital, in Canada, scores of hospitals get hacked and are held up for ransom. So this is becoming an increasing problem. And there are undoubtedly many other applications where interactive machine learning will be useful. So I'm optimistic for the future in terms of the role of human factors and human-computer interaction, but I'm a little bit nervous about what our world's going to look like, and what's going to happen to the college undergraduates, the university undergraduates of the future, and how much they're going to be able to learn and know. Okay, so I'm going to stop there and hope there's a little bit of time for discussion, Alona. Apologies for taking a long time.